I argued that because of angular momentum, centrifugal forces acting, for example, here in this sketch, we'll not end up having material just collapsing radially onto the star, but actually much of this material, or at least a fraction of it, must go into orbit because it cannot really fall down and it has too much angular momentum. So we form something that looks a bit like a disk. There's an axis, a rotation axis, and some of the material ends up in orbits around the disk. Let's go away from math and physics and just actually look at what these disks are. They are there and they're very well being investigated. They have been investigated. There's a lot going on at the moment as well. For example, with James Webb Space Telescope, there are lots of news. I'm not showing them now today. Much of this is going on, so wait for publications. This is how they look like in a sketch. Again, as you remember, we have gas and we always have solids as well in the disk. It's still there, there's dust. And this cross-section shows you a bit how a disk is structured in terms of the solids. There's dust, but they're also growing pebbles. Somehow we want to form a planet. I'm not doing this. This will be the subject of tomorrow's lectures. We have many things going on here, dust settling, dust growth and whatnot. On the other side you see the structure in terms of gas. It's also a vertical structure. It's in fact, normally the situation is such that the surface of the disk is warmer than the midplane of the disk, and that's simply because of stellar irradiation. You radiate the surface of the disk and make it warmer than the midplane. So depending on where you are, you may have ices, molecules that freeze out and become ice, like water ice. You have other molecules forming in the middle region here, and at the disk surface you can have temperatures that even destroy molecules or even ionize. It's not the temperature itself, but the radiation coming from the star can even ionize some of these atoms or molecules. So without going into more detail, coming back to some of it, also about the central star, by the way, you see here a picture, a sketch that shows magnetic fields of the star. They matter as well, as I will come back to and explain a little more detail. Here are disk observations. This is just one disk seen at different wavelengths. You see here a disk, a very beautiful one, it's the closest disk to the sun. You see it just we happen to be along the, our line of sight is just the polar axis of this system. So we look down onto the disk. This is in the near infrared. And what you see here is actually not the radiation from the disk itself, it's scattered light, starlight that gets to dust and is scattered by the dust. And you see basically that in this wavelength. The interesting part of this image is, in fact, it's not just a disk, a flat disk. It has gaps. It has a gap here. There's something more closer to the center. You hardly see it. There's another disk there. There's a gap and there's another gap. And you wonder what these gaps actually are. And the speculation is that planets are forming in these gaps and they wipe away all the material. This is the same disk, but now seen in millimeter wavelength, and here you see the radiation from the disk. It looks very different. These are partly larger bodies, not the very fine dust, but pebbles, you see them here. So they don't have to be at the same location. It's not, depends on what your dust, how your dust is structured. And this is the gas disk. You see, this is much bigger. That's a tendency we see that gas disks are a bit larger than the dust disk. Maybe dust is moving to the central star more easily. It's a carbon monoxide millimeter observation of showing the gas component. These are very big, these disks, or this one disk, so something like 200 AU. Remember, Neptune's orbit is 30 AU, and these disks can be quite a bit larger. More examples, just for the fun of it, you see many structured disks with gaps. If you can see it just barely maybe, this looks like a spiral. In fact, some disks have spirals like galaxies. It can be explained, it's an effect of self-gravitation or another object sitting outside and creating instabilities and forming spirals. This is a more homogeneous disk here. Here again, a little bit different. This was a millimeter, these were millimeter observations. You see the radiation from the dust. Here is again scattered light in the near infrared, very funny structures again, lots of little gaps here. And you see a dark band. I come back to that in the next slide, I guess. Oh, not quite. There's a lot of discussion about this disk called PDS-70. It's a keyword presently that is making a lot of waves. You see a disk, but a lot of the material seems to be, well, at least part of it is gone here. We have a gap. There's again a disk in the center. This is not the star really, it's another disk that is, sits in the center, and of course there's a star, but you don't see it here. But the most amazing thing in this is that you have a planet. Indeed, you have a planet here that is in the formation process. As I said, I'm not talking about planet formation, but here you see it in the disk, there's a planet. There's a second one somewhere down here, which is not visible here. And the interesting point is that this planet, which is a giant planet, like, you know, several Jupiter masses maybe, it has some fuzzy stuff around it, which is again a disk around the planet. So the same repeats now. The planet also forms a disk, and it takes its material from the protostellar disk outside here. So it's the first time that this has been seen, that the planet, first of all, we have planets in disk, and second, we see even how they accrete and grow. So this is a key observation and a key object of study at the moment. Totally different here. These are disks seen from the side, edge on. They have funny names like Gomez Hamburger, you can see why. This is the flying saucer. There are some others, you know, they're very nice. And you see the structure of the disk. In fact, you see how the disk becomes thicker far away from the central object in all cases. And I argue why this is just in a minute. There's something interesting also in this case. You have actually the disk here. The bright stuff you see is scattered light from the star at the disk surface. So you see the disk surface here bright because there's scattering of light, while most of the disk appears dark. That's really where the mass is. It's not transparent to this light, to optical light. You see also this green jet. Jets are ejected from forming stars. I come back to that hopefully later in my presentation. This has become the most famous protoplanetary disk. It was observed about 10 years ago by the then new ALMA observatory in Chile, radio observatory at millimeter and submillimeter wavelength. You see here a lot of gaps, and that is the solar system orbits out to Neptune at the same scale. And it's sort of, you know, you get motivated to think, well, maybe these are all planets forming there and forming a planetary system. We don't know yet, but jury is out and we'll see. Good. In the disk, we should not forget there's always a star in the disk. And we now take it to somewhat later times now. We don't care about this envelope and collapse anymore. Let's assume it succeeded forming a protostar. And eventually the clouds go away because there's simply no mass left. It's all accreted. Or in some cases also the radiation and the outflows, the jets from the star may also destroy some of the envelope and disperse it. So what we have in the end is indeed a star in the center and surrounded by its own disk, like this one here. And the disk, maybe planets form. So it's a sketch, of course. And when you go really close to the star, what we see there, that's again a sketch. Here's the disk, a cross-section of the disk, star. You need to see how this looks like. And the star has magnetic fields. All these objects have magnetic fields, a bit like the sun. The sun is also a magnetic star. And field lines now may attach to the inner border of the disk at some point. You know, they connect from the stellar surface, there would be spots, magnetic spots, like sunspots on this star. You see it here in the sketch. And they would connect to the disk. Now, the disk accretion process, I haven't talked about this yet. There's mass coming in from the disk along the radial direction and eventually hits these magnetic fields. And magnetic fields would then take up the mass and let it fall down along the magnetic fields onto the star. And that induces, shocks on the surface of the star. And these shocks are sources of ultraviolet emission. That again is actually important. That will be emitted again, and it's important to drive chemistry in the disks. So you see this process of accreting material from the disk indeed has a back reaction on the disk, and I come to that, back to that a bit later through ultraviolet emission. T Tauri stars do not yet have the normal nuclear reactions as we know them from the sun. They're not burning hydrogen. They're still contracting, so they tend to be larger than our sun. If they end up as a star like the sun, they're larger, 2, 3, 4 times as large as the present sun, but they're contracting. And that's where they gain their energy from. So they look like stars. They can have surface temperatures like the sun, 4,000 or 5,000 Kelvin. They have their magnetic field, so very similar to a star, but no hydrogen burning in the center yet. This is a sort of a snapshot from simulations of accretion. You see magnetic fields. You see the inner border of the disk, and the simulations take it from there and simulate how the mass drops onto the star along the magnetic field lines. It's a very dynamical process and needs to be simulated to show you what's coming out. It depends on the parameters like magnetic field, rotation rate and whatnot, and so you see different possibilities here. These accretion streams produce hotspots on the surface, and as I said, there's a lot of ultraviolet coming from those sources. Again, here in an artist's view, the disk, the magnetic fields at the inner border and the star. I should also say something else here. This is shown by this sort of rim. At some point, if you go too close to the star, which is now some sort of real sun-like star, not quite yet, but it has a surface temperature like the sun. At some point, you're too close to the star for the dust to survive, and that happens at about 1500 K. Your dust is destroyed because it's becoming too warm. Dust cannot exist beyond 1500 K approximately. And then it evaporates and goes into gas phase. And that's what this shows here. You can still have the gas going closer to the star, but you won't have dust. Stars are magnetic, as I showed. It's very similar to our own sun. This is actually from observations. You see a map. There's a possibility, there's a method to map the magnetic fields on a star, even if you don't resolve the star, but you do spectroscopy, high-resolution spectroscopy, and you can find out how the magnetic field is distributed on the star. And then you can calculate how the magnetic field lines would look like, and so you see some field lines are closed, like on the sun. This is now an X-ray image of the sun, where you see the magnetic field lines, sort of, That's plasma that is contained in the magnetic fields. Very hot plasma, that's a solar corona, 1, 2, 3 million degrees. You can see it only with X-ray telescopes. Also here, you see these closed magnetic field lines that are modeled here. And some field lines are open. It's also true for the sun. And along these open field lines, you have the solar wind escaping, or part of the solar wind. And so we'll probably also have stellar winds driven by the stars, by the magnetic fields. Good. So these are called T Tauri stars because the first of its kind is a star called T Tauri. This is the stellar designations, they sound like that, in the constellation of Taurus, in this molecular cloud that I showed you at the very beginning. So this is a class of stars, and there are many of them. And they have disks, as I said, normally, most of them. Good, so let's go back a little bit again to the discs themselves. A little bit of theory. You saw this Gomez hamburger and the flying saucer, and they looked a bit strange. They got thicker to larger distances. Let's analyze why this is. It's actually quite easy. So in a disk cross-section, here is a star, and that's sort of the disk here, as we saw it already, very simplified. It's coming wider, large distances. So let's take a mass element of the disk somewhere here, and let's check the forces that act on it. The disk is stable, let's assume, right? So what you have is, of course, again, gravitation. This gravitational force between this mass and the star. And it's going along this diagonal line. Now let's just not, the horizontal part, the radial part of this force is balanced by centrifugal forces because these gas masses are in orbit around the star. In fact, they're Kepler orbits approximately, like, the planets in the solar system. So the radial part we're not interested in at the moment. But let's check the vertical part. Now, this is not quite plotted quite correctly here. This vector, this acceleration vector, force vector, has a component in vertical direction, which is of course smaller than shown here. And well, it's easy to quantify it because we have Newton's law along this line. The complete gravitational force is G times the mass of the star, mass of this element, divided by the distance squared, which is r squared plus z squared. And then we need only the vertical component, that is a ratio of the total force of z divided by this length squared and square root. We can do some approximations of this because z is much smaller than r. You can simplify this expression. I'm not going into this because I promised not doing mathematical derivations here. But you can, this is easy really. And then we have another force because we have balance, pressure bands actually, because there's also pressure, because these disks have a gradient in pressure. They're denser inside, less dense at the surface. This is the same thing as a planetary atmosphere. We have hydrostatic equilibrium, high pressure here, low pressure higher up, and you can calculate what the profile is, the density profile. And so this is simply dP or dz. Should be a density here as well, I'm sorry. And we can solve this equation because it's a differential equation. And we solve it and find the pressure profile, the density profile, is also pressure profile you can derive from this. And what you find is the density or the pressure is highest in the midplane of the disk, in the equatorial plane, and gets lower and lower. And the profile is a Gaussian function, e to the minus z over z squared over 2h squared. These are components that you need to formulate what h is. H is this expression here. It has the thermal velocity, it has the sound speed, sorry. It has omega, the angular velocity. Cs squared is a function of temperature. And so you see what you need is a temperature profile, you need omega, which is, like in Kepler's law, a function of the distance from the star. And you mix all of this. I don't want to go into any details here. Here's a temperature profile that is typical for disks. Function of radius, temperature gets lower and lower if you go farther and farther away. This is Kepler's law. Omega goes with the r to the minus 3/2. You put that in and you get, for h, which is this term here which gives the thickness of the disk. It's called a scale height. And this increases with something like r to the 1.2. So you see, the farther away you go from the star, the thicker your disk becomes like this. And that's what you see in these pictures. So that's a very short explanation why we see this widening of the disk, widening with distance. I have already said something about Kepler's law. I need to say it, of course, now, but most of you know those laws, but just a repetition. Any orbiting gas molecule, like any planet, in the orbit around the star is subject to force balance between gravitation, attracting force between the particle and the star, and the centrifugal force, which goes with v squared over r. We can solve this equation for v, which gives us the orbital velocity. We can solve it for period as well, which gives us the orbital period, and you get, you can calculate planetary orbits that way, the velocity of a planet, if you only know the solar mass, stellar mass in the center, and your distance. This is Kepler's law, and the disk essentially also follows a Kepler law. Not exactly, but it's very close to that. But there's a little correction to be made, but I'm not going into this. Good, I come back to that shortly a little bit, but let's now see where we are. Let's recapitulate what we've learned. This is a timeline, and I collected some pictures, and there's nothing in pictures here. I want to go toward classifying what we've seen, because that comes up in the literature all the time. These are expressions that are very well known. So we started with a core, a dense core that has no star. We eventually went to collapsing cores that may have a protostar. You see, this is not in the center here. It's quite a bit offset. What can be in the center can be offset here, like this one. Eventually, after the collapse, we form a disk. We had that. Of course, with a star in the middle, a T-Tauri star, as you can see it down here. And then that's for later in my presentation. The disk will disappear at some point for various reasons, and we're left with just a thin dust disk or nothing. And what happens in the course of evolution from left to right is, well, you see outflows here, you see jets. Some of the material that drops onto the star is actually re-ejected in jets or in outflows. A very beautiful example here. In later phases, when you have a disk, in fact, you have disks already here when the star is only forming in the core. You already have disks there, and somehow in this stage you begin to form planets. It's for tomorrow to discuss. And later you hopefully manage to get the planetary system, because once the gas is away, it's gone again, and it takes only a few million years. Then you have to have formed your gas giant planets like Jupiter, because later than that, after that, there is no gas left anymore. So you have to form planets quite quickly. You have a bit more time for terrestrial planets. But anyway, here's a planetary system indeed. 4 planets here, you can see, and a central star. Good, just for completeness, these classes have historically been named as class 1 protostars. The next stage, when the cloud is gone, we're just left with the disk and the star. Class 2 T-Tauri stars. So a T-Tauri star is a class 2 star. Class 3, when the disk is gone, can also be called a T-Tauri star, as long as it's still contracting. There's something in between, a transition disk. Come back to that a bit later again. And so, at some point, people found, well, there's something before class 1. Unfortunately, the names were already given, class 1, 2, 3. So they had to find a name for the stage before the collapsing phase. And so they're called class 0s. There's no class -1, as far as I know. Good. Now, how do we observe them? I showed you a few pictures already. We can go a bit deeper into this, also in the classification. Because if we don't have pictures, we have spectra. We still have the light that we collect, and we can make spectra out of the light. And maybe they tell us something as well. And indeed they do. If you go back to a disk like this one, as I already said, of course, obviously it's the warmest closest to the star, and it's cooler further away. Now dust radiates like a black body, like most of the objects in this room. It has a temperature at the surface, and it radiates according to that temperature. And the spectrum that it emits is given by this Planck formula. It's a black body spectrum or a Planck spectrum. And that was found by Max Planck in 1900. As by the way, also this was the start of quantum physics. I'm not talking about this now. But the spectrum is given for every object here in this room. It's given by a function that's only a function of temperature for any given frequency. You can translate this to wavelength, of course, the frequency of radiation. And they're all constants, Planck constant, Boltzmann constant, speed of light, but it's essentially only a function of the temperature. The spectrum is given once you have the temperature. They look like this in a log-log plot. This is frequency here, the light's frequency. This is the spectral energy density. These functions increase like frequency squared with increasing frequencies. So it's getting brighter the shorter wavelength we go, but there must be a maximum. And that was indeed the finding that Planck made at the time. So there's a turnover and then there's a rapid decrease here toward shorter and shorter wavelengths. They only depend on temperature, as I said. Depending on the temperature you have, the spectrum moves, the peak of the spectrum moves in frequency or in wavelength. The hotter you make the spectrum, the shorter its wavelength, the shorter the wavelength of its peak is. So if you have a cool object, it radiates mostly in infrared. Then it comes to near infrared. If you make it hotter, it becomes visible, like a star, like our sun. And then you drive some of the radiation into the ultraviolet if you go 10,000 degrees or more, as some stars are very hot, like tens of thousands of degrees. So now we can at least qualitatively apply this to a disk. So let's go step by step. What we have to do is we take a disk, it's a very simple disk, a flat disk here, just a plane. This is an element of surface in the disk at the distance r. And then we have the star that irradiates the disk. So all the energy comes from the star in this picture. Now, this is again a calculation where we need to analyze an equilibrium. Radiation in must be radiation going out in terms of energy. Otherwise, you accumulate energy there. And in an equilibrium situation, that should not happen. So it's just geometry. You have a distance, you have an angle here, and you can analyze how much energy hits this element and is absorbed there and warms the dust. But then the dust has to re-radiate this energy according to the Planck formula. While the incoming light can be optical light, the outgoing light corresponds to the temperature of the dust. And so it will be a Planck spectrum, and that can be mostly in the infrared. Because the temperature of the dust will not be the same temperature as the star has in the photosphere. So this can be calculated analytically, it's not very difficult. And you find that the temperature decreases with distance as about r to the minus 3 over 4. If you do it a bit more carefully, you've seen that the disks actually are not flat, but they have this sort of parabolic structure. It's a bit more complicated to find the equilibrium here and formulate the run of temperature. What we find is T goes with the inverse of the square root of distance. So you see how a disk becomes colder. At least the disk surface that's irradiated by the star gets colder and colder further out. Now you can go back, and we do this just qualitatively. We look at the broadband spectrum. This is 1 micrometer, is now wavelength. 1 micrometer, 0.1. This is ultraviolet. This is a little optical range that we have from blue to red light. Near infrared, 10 micrometers, 100. Sub-millimeter here, and millimeter wavelength. So this is the whole spectrum of a disk. And what we see, and I show you observations, but this is just a sketch to begin with. Now, what we expect is, well, we'll see the star. The star has a blank spectrum corresponding to maybe 4,000 or 5,000 degrees, like our sun. And that's this red Planck spectrum, black body spectrum. It's not exactly a black body. There's a lot of lines, absorption, and I'm not going into those details, but roughly it corresponds to a black body. It's really not a black body on this side, but it's similar corresponds to a black body if we don't do the atmospheric analysis here, where you have absorption. Now the dust in the disk is distributed in temperature from maybe 1500 K at the inner border to maybe 100 K. And all these rings of dust produce Planck spectra, one after the other, but they are shifted against each other in wavelengths. So we add up short wavelength spectra from the inner border of the disk, that's this part. Then intermediate, we all add these individual spectra, and then the coolest part of the disk, which is typically the midplane far away, they add the longest wavelength spectra, so they are all black body spectra summed up. And there's some features that are not due to black body, but some other stuff. Come from dust, it's actually dust emission. So this is the typical appearance of this combined star-disk system. The star at shorter wavelengths in the visible range as well. And then the disk in the infrared. That's what you get. This whole thing is called the spectral energy distribution, and we learn indeed from the spectral energy distribution how the disk is structured, what the run of temperature is from inside out, and of course also we can actually see maybe where the inner border is, and I'll show you examples on this. These are real observations. You see SCDs or spectral energy distributions here from ultraviolet to about millimeter wavelength. You see the star here. This is of course really measured at this range. Then this is a model because at about a micrometer or a few micrometers, the disk is now the brightest part of the spectrum. So this is all from the dust emission. You see a very broad spectrum that comes in addition to the stellar spectrum. So this is actually a model for the star, and this is the actual observation dominated by the disk. This is a typical standard disk. You see also the image of the disk. It's not much structured. There's a little bit of a gap here, but overall it's filled. Now there are also spectra like this. There's something missing here if you compare it to the first picture. There's, by an order of magnitude, there's missing emission here. That's a certain wavelength range, obviously. And that corresponds to a certain temperature range via the black body emission, black body formula that we discussed. And so it seems there's some temperature range is missing in the emission spectrum. And that corresponds indeed to a gap in the disk at a certain distance. You see this gap here inside. There's a bright disk here, and inside it's dark. There's not much dust there. And so you can use the spectrum to see these gaps without actually getting an image. This is called a transition disk. Apparently it begins to dissolve. Somehow the material is carried away and it's evacuated. There's a similar thing here, but it's not quite the same. You see, compared to the upper disk, that there's also an excess emission here from the disk, but it's actually quite faint. Drops rapidly. It's not so much as here. Here, the dust is depleted everywhere in the disk. You see, at every wavelength, you get lower emission. So that's another type of transition disk that just sort of disappears everywhere at the same time. So now we can conclude our classification scheme. Let's recapitulate what we had. We started with a stable core here, dense core, a collapsing core. Then we had a collapsing core in which a disk started forming because of angular momentum conservation. The envelope disappeared, and then we had a Tittori star with a disk. And finally, the disk goes away. So, if we look at the spectrum, what do we expect? Well, first of all, these initial clouds are very, very cold, 10 K. There's not much else there. And you get a black body for 10 K because of the dust that's embedded in this cloud. Even if the protostar slowly begins to form during the collapse, the spectrum is completely dominated by this cold dust. That makes still the black body spectrum in the far infrared and sub-millimeter range. There's nothing in the optical. The optical range would be here on the left side of each plot. So you see nothing, they're dark. A bit later, well, I should proceed here. A bit later, you have a protostar that begins to warm up the innermost material. The envelope and the forming disk become warm because the star itself also becomes warm. So you find a second black body from the inner region of the protostar, and then an excess, from a colder cloud that's still out there. So the spectra become broader, they approach the optical range, but not quite yet. And in the next stage, that was the Titori star, when the envelope was dispersed, we have only the star. Now we have a black body spectrum from the star, and then the SCD, the disk spectrum, in addition to it in the infrared. And finally, we are left with the stellar spectrum and a little bit of disk, and that disk part goes away as well. And again, this is a classification scheme, class 0 here, called black body. Class 1, you begin to see a disk and the inner warm region. And then the class 2, where the optical star becomes visible, and the disk, and the class 3 stage after the disk dispersal, when we hopefully have a planetary system. Good. This is all sort of general, but do we actually know anything about the disk of the solar system? Well, we have a little bit of evidence, but of course it's gone, right? I mean, it's difficult to say what it was. Surely it was there because we have planets. Now, there's a trick to find out a bit more about it. And that's what is called the minimum mass solar nebula. I can actually estimate what it at least was, how much mass there was at least. And the game we are now playing is the following. We take our planets. Obviously the planets were formed in the disk, and they use disk material. We take each planet, for example here, Mars, and then the next one is Jupiter. And we first analyze their composition and would like to see how much mass was there to form that planet initially in the disk. Now, the Earth is made of silicates and whatnot, heavy elements, but the disk initially was mostly hydrogen, right? We don't have that hydrogen here anymore. So we complement the present mass of the Earth by all these elements that are apparently missing to get back to the initial composition of interstellar gas, which is the same as a protoplanetary disk. So we have to add, we know how much it has to be, given the content of heavy elements here. We add the missing hydrogen and the missing helium, for example, to Earth. So we had a higher mass for Earth. In Jupiter, it's the same. Of course, Jupiter still has a lot of hydrogen and helium, so there's less of a correction to be made. And now we crunch those planets and destroy them and distribute the mass, the entire mass of the planet, in an annulus, in a ring of around the orbit of each planet. Let's say the annulus goes from halfway between the two planets out to the halfway between this planet and the next inner planet. So we distribute that mass, and finally we analyze what the density of each ring is, and smooth it a little bit, because there will be a step function which is a bit weird, but we have to smooth it and get indeed this. This is now what we would get as a so-called surface density. That's basically collapsing the whole disk to a plane. It's just a two-dimensional plane. And measuring how much mass you have per square centimeter after the projection. So that's the surface density as a function of radius that we assume must have been there in the initial solar system to form our planets. If there had been less, we would not have the mass that we need to form our planets. And what you find indeed is that the density decreases with radius with a slope of about -3/2. That's for the gas. The solids are just 100 times less, standard. There's a little correction to be made, because inside this radius, the solids further out may have ices as well, which are also solids. And inside this radius, the ices evaporate sublimate and go into gas form. So there's a little correction to be made. But this is what you find for the minimum mass solar nebula, and you can integrate this distribution from the inside, from the inner radius to the outer radius, and you find a total disk mass that our protoplanetary disk must have had initially of 0.01 solar masses. Of course, that's needed anyway to form our planets. We need to have enough mass, especially to form Jupiter and Saturn, for example. So that's what we can find out just by simple analysis. Good. Let me talk a bit about other aspects of disks. Less physics, but there is also chemistry going on. We have molecules there. We can observe them now. And I know there are a few astrochemists among you. I'm not one of them, so I will not say in too much. But I show you what can be done and what people modeling disks in a chemical way, what they can produce. Now, let's go back what we need. Here is a cross-cut through a disk. We have ices, perhaps, in the midplane. We have warmer regions above, and there's a lot of chemistry going on there because the temperatures are right, the elements, molecules are there, and they drive chemical reactions. Now, before we do a chemical modeling of such a disk, what we need to know, of course, for a specific case, we need to know the mass of the star, because it also determines the shape of the disk. We need the irradiation that comes from the star, so we need to know the stellar spectrum or the effective temperature of the star. We need to have the ultraviolet field. It cannot be just predicted. We need to measure it. Depends on the accretion rate onto the star. We talked about those hotspots. We need to know what the mass of the disk is. It cannot be predicted again. You have to measure it if you want to model it. The disk radius, inner and outer radius. A prescription for the disk scale height. You saw that disks widen with increasing radius. The gas to dust mass ratio, which standard would be 100, but it can be varied. It doesn't have to be exactly 100. Dust size distribution, which I already mentioned. And then the composition, roughly speaking, what you have already in the disk. You can add dust, of course, silicates, carbonates. These are the inputs that you need for the model. And then, of course, you need to also have abundances. You need to tell the program that does this, what abundances of elements you have. For example, here, you don't read this. It's just meant to impress you, not for you to read it. That's why it's so small. In this calculation, 12 elements were used. There are more, but these are the essential elements you need, C, NO, sulfur, silicon, and whatnot. And these are the molecules you want the code to deal with. You can have more, of course, but these are really important molecules you want to calculate. This is said to be a small chemical network. You then calculate chemical reactions that are possible within this set of molecules and abundances. You can have much more, of course. You can have very big, but it just takes more computing power, of course, to find any solution of the model. So you throw that into a code, and what you get are models, indeed, that predict how the disk is structured chemically. This is an example here. It's a crosscut, radius, vertical direction. It's actually not exactly vertical direction. It's always Z. That's vertical. That's the vertical distance divided by R. R is given here. That's a radial distance. So it's not exactly the geometry that you see here, but it's renormalized by dividing by R. And also this is a logarithmic scale on X, so that is a linear scale. So you do not exactly see the shape of the disk. But you can find out from such models where CO gas is. CO is, for example, very widely distributed from the inner disk to the outer disk, but then there's missing CO here. Red means it's the maximum amount of CO that you have in this model, 10 to minus 4 times the hydrogen density. But there are gaps, right? But then you look where CO ice is, where CO has condensated to ice mantles around dust grains. And you find this, that's just complementary to what you have here. So CO is either ice or gas. And there are other things happening also, destruction through chemical reactions. So you may have other reasons why a molecule is abundant or not, but here it's ice formation. Or for example here, water ice. Where do you have water ice? Well, you have it everywhere, and it's ice around dust grains. But you don't have it in the inner disk. There's a line here, and there's no water ice. Why do you not have water ice in the inner disk? Well, because the water ice sublimates. It's going into vapor, into gas form. You can see some of these processes indeed in the spectra. This is an example spectrum taken a while ago. Now James Webb Space Telescope continues such studies in much more detail. But this was certainly a very interesting observation. We now get such observations with James Webb Telescope as well. You see here in the infrared a lot of emission lines. So these are transitions in the molecule that emit at certain frequencies. Also atoms or even ions, you see. This is actually from an ion, neon 2. Means neon that was ionized once, so there's one electron missing. It's charged, it's a charged particle of neon. Now all of these features that you see here, all these spectral lines in the mid-infrared, they're all coming from water. You actually see the water molecules here, and they're all in gas form, of course. There's also some OH molecule that is important in the formation of water. It's very close already to water, because water just needs one more hydrogen atom. Then you see organic molecules in this range, and there's more and more we see in James Webb data, like C2H2 benzene and others. So you can really analyze composition and compare with your models, the synthetic models that I showed you before. I talked about these transitions, ice lines, just in a slide ago. You know, if you get close to the star, ices cannot exist because it's too warm outside. It's too cold for molecules to exist in gas form, and they freeze out on dust grains, which can be observed. And I want to show you an example really that shows this explicitly. We are looking especially at ice. The separation line, it's not a vertical line, but it depends a bit on at what disk height you are. It's warmer at the disk surface, colder in the midplane, so this is a bit of a parabolic shape here in this sketch. Midplane, you have this separation line closer to the star than at the disk surface. And, you know, this is just showing you where these ice lines are, or snow lines as they are called, depending on what molecules you're looking at, like water, carbon dioxide, carbon monoxide. The sublimation temperatures of these molecules are, for water, about 150 Kelvin. It depends a bit on the pressure you have. It's not a unique number. CO2 is about 50 K, and CO sublimates at a very cold temperature of about 20 K. So the corresponding radii in a typical T-Tauri disk are 2 astronomical units for H2O, 10 about for CO2, and 45 for CO. Now that matters, especially when you look at H2O, at water. We have water on our Earth, right? It's actually not much. The Earth is a relatively dry planet. Nevertheless, we have water. But when Earth formed, it formed out of the solids. Now the solids had, when you look at this, where the ice line is for water, 2 astronomical units. At the place where Earth presumably formed, the dust was dry. It didn't have water. So you go into very important questions here about habitable planets, because you want to have some water on a planet. The Earth did not accrete a lot of gas. It accreted really the solids. It accreted some gas as well, but now comes the question whether you have enough water or not. And you see that in the solar system indeed. The inner planets are relatively dry. Even the Earth is not a very massively humid planet. This water is only on the surface. Well, there's also some in the mantle, but there's a concentration of water on the surface. While if you go into the outer solar system, beyond the 2 astronomical units, you have asteroids that are very water-rich, or Saturn's moons, for example. There's a lot of water in these bodies. They accreted also the ice. So you see planet formation depends on those ice lines. And they are located at different distances. So what your atmospheric composition, especially the atmospheres, will be at the end, after the planet formation, depends on where you form a planet. Whether you have water or not depends on where you form a planet as well. And that's much to do with these ice lines here. This is an example. This is a protoplanetary disk seen in dust emission. There's no structure here, but if you look at the CO gas, this is from an emission line of CO, most of the CO is concentrated inside this faint red radius, this circle here, where it's dark blue. That's where you see CO gas, carbon monoxide. In this picture here, the same disk observed in N2H+. This molecule also has its spectral line. And you see there's a lot of N2H+ outside this red circle. Now, why is this? Well, this is because those two molecules don't like to coexist in gas form. They chemically react. You can have N2H+ only in regions where you don't have gas phase CO. And so you see how they separate really along this red circle. Inside you have gas CO. Outside you have only ice, CO ice. And that's where N2H+ can exist only. So this is very clearly visualizing one of these ice lines, the CO ice line. Why does this have consequences for planets? This is a quite simple example, but I think it really illustrates what is important here. This is radius, distance from the star. That is the important C/O ratio, the abundance ratio of carbon compared to oxygen, carbon to oxygen. Not atoms or whatever. It's the total number of atoms in any molecule of C divided by total number of oxygen atoms in any molecule. Now, if you start with a certain ratio, like in the solar system, actually, it's about 0.55. That's what you expect. The overall ratio. Let's start here in the inner solar system. There are also, of course, other molecules, so I don't show all of them. We just assume now that there's H2O, CO2, and CO. And as we move out, we eventually condense H2O onto ice mantles. So the gas phase C/O ratio gets higher. Why is that? Because we take oxygen, in H2O there's oxygen, and we condense that. So that's missing in the gas phase. So the ratio goes up. Later CO2, the same thing. Now we remove C and O, but there are 2 oxygens for each carbon. And so the ratio of C/O goes up again. Stays here, and then there's no gas phase anymore, because at some point we condense all important molecules. And then you go back to the initial ratio here. So you can analyze this, of course, ice line after ice line. And now it depends on where a planet forms, what sort of gas phase molecules it collects. So what you see as an atmosphere around the planet may now depend on this ratio, the C/O ratio here. That also influences the atmosphere. It depends on where you are in the disk. The disks also, of course, have dynamics. They are not staying there forever. And what I want to show here, and I just briefly explain it, we showed that the disk is following Kepler's law of rotation. Disk parts that are closer to the star rotate faster than disk parts further away, like planets do. Now we have not planets, we don't have planets here, but we have a fluid, we have a gas. And now you have a ring of gas that has its rotation speed around the sun or around the star, and the next ring has a different speed, and that means you have two gas streams or two gas rings that are next to each other with different velocities. And that induces something like friction between the gas. Between every shell, every ring has friction with the next ring. That's a process that we describe as viscosity, whatever viscosity is. And viscosity leads to, this is the friction force, just for basically what I tried to explain just before. You have a ring inside that is faster, and then the next ring is slower, smaller velocity further out. And the outer ring, which is slower, tries to decelerate the inner ring, tries to break it. While the inner ring that is faster tries to accelerate the outer ring so that they come to the same velocity. Of course, they don't manage to do that. What's indeed happening is that the frictional force here at the faster inner ring is against the velocity vector, so it tries to break. And that means that you transfer angular momentum here. You take angular momentum from the inner ring, which rotates rapidly, but you try to break it. And that angular momentum is taken away from the inner ring and transported to the next outer ring. So you transport angular momentum from ring to ring. But the inner ring loses that angular momentum. That means that its mass loses the angular momentum, has to fall toward the star into a closer orbit. So this process essentially means you transport angular momentum to larger distances, and at the same time you transport mass to closer to the star. That's a bit simplified. It's actually not exactly correct. You do not transport all mass to the inside and all the angular momentum to the outside. You know why? Because somebody needs to transport the angular momentum itself. You need mass to transport the angular momentum, and so you actually, part of the mass will be transported to larger distances, while the dominant part of the mass is approaching the star. So it's actually a diffusion process, and it goes both ways, but most of the mass goes toward the star. The angular momentum is transported to the outside. This is viscous accretion, just explained in words. I'm not going into calculations here. You see it, I wanted to do this very briefly only. A calculation of this process. This is a cross-cut through a disk. It's again this surface density. You see radius here, all logarithmically shown. The initial profile of density versus radius was this, so a disk with a decreasing density and then a cutoff. And as you let this evolve through viscosity, this friction process, you see that, first of all, the mass decreases everywhere apparently, but that's because it's transported inward and eventually gets lost onto the star. But some of the mass is actually transported away from the star. So this is this spreading here of the disk from, in this case, 10 to several tens of astronomical units. But it's a smaller part of the disk mass. Most of the disk mass is actually transported toward the star. Good. That one, yes. So we talked about viscosity, and nobody really figured out what this viscosity is. You can have friction between molecules that collide, molecular viscosity. It's just shown, it's an easy argument. It's by no means sufficient. You don't manage to get any accretion that way. Then other ideas came up, like magnetic fields, turbulence in the disk, because magnetic fields also mediate between one particle and another. So maybe you can use that, and that's been very popular as well. And then there are other ideas for viscosity. It's become very complicated, but you can do something completely different. I'm showing you that here. It's almost trivial. Take a magnetic field line. It's attached to the disk. Here's a disk, just schematically. You have a magnetic field line, and these field lines, in fact, rotate to a certain extent rigidly. You know, they go with the disk. Now, if you have slightly ionized material, you take a little parcel of material and lift it onto, you know, at the disk here, you lift it onto the magnetic field. Now this parcel can slide along the magnetic field with no problem. Once you manage to put it on a magnetic field, there must be a certain inclination of the magnetic field line, otherwise it doesn't work. If it's too steep, then it doesn't work. So you let it slide, and it goes further and further away. Now, what happens? I mean, I'm trying to do. I brought an experiment here. It's a theoretical experiment. A pencil, like, you know, theoretical physicists use pencils. And there's a ring, there's a mass, the keys. Now, I'm not sure. I haven't tried this actually. So this is my magnetic field line, and this is the ionized. It's not actually, but this is the ionized material that I let slide. Now I'm trying something. You know, I do the rigid rotation, so I hope this works. I do this faster and faster, and what happens? There it goes, right? Now, what you did not see, this actually braked me slightly in my motion. It took angular momentum away from me. The angular momentum is now gone. I need that key again. So what happens, and you know, this is easy to understand, the angular momentum the parcel had here at the start is obviously, it's just the formula, mass times the angular velocity, omega, times r squared. Now, if this is rotating rigidly, as magnetic fields can do for a while, the omega is the same, the mass is of course the same, but by necessity, the angular momentum now is m omega r squared at this distance. I call it already Alfvén distance. Come back to that. So, because this radius here is larger than this, and you even have to take the square, we have a lot more angular momentum out there in this mass element. But it has to get the angular momentum from somewhere, because angular momentum is conserved. So where did it get it from? Well, it got it actually from the next ring of mass here at the point where the magnetic field is attached. It removes it from there, takes it with it through the magnetic field line, and then eventually, like here, moves away, gets lost. So you extract angular momentum by this process from the disk. Now, Alfvén radius, just very briefly, at some point you saw the pencil had a certain length, and then, you know, material got lost. That's also happening to magnetic field lines, although they don't have an end. But when you have, it's basically the magnetic energy density of the field divided by the kinetic energy density of the flowing mass. If the kinetic energy density is too much, then this breaks down. This doesn't work anymore. Then the magnetic field line will not co-rotate anymore, it becomes bent, and the mass flow actually dictates where the magnetic field lines have to go, like in this little experiment here. So you can actually, if this is called the Alfvén radius, if this is large enough, you can transport quite a bit of angular momentum, and you remove it from the disk. And of course, if you remove angular momentum from the disk, then the disk has to, you know, move toward the star because there's missing angular momentum. So this may also explain accretion, very roughly speaking. This has been very simplified. But funnily, this mass that moves away from the star has to go somewhere, right? And here in this movie, you see where it may go to, namely into a jet. And these things are everywhere now. In protostars, you see jets all the time. And that may be exactly this outflowing mass that's coming out here. A simple analysis will tell you that the mass loss rate in the jet compared to the mass loss in the disk that eventually will end up on the star is given by the ratios of the radii, inner radius to Alfvén radius squared. Observationally, what you find is that the mass loss rate in these outflows or jets is about 10% of the accretion rate toward the star. Luckily, it's not much more because you don't lose all material. Most of the mass is still going to the star, and a part of it is ejected. So that's the present idea that you can do angular momentum transport that way with magnetic fields, and you even form those jets that are so well observed. That's a different problem that has been known now for about 30 years almost. I talked a little bit about luminosity of protostars. They can become quite bright, they are bright. But when you observe them really, protostars of class 1 essentially, they are underluminous by a factor of about 10. From theory, if you develop any of these collapse theories and accretion processes, they're underluminous. They should be brighter. And it's very systematic. That has been called the luminosity problem. You find literature back into the 90s. This was heavily discussed at the time. So the idea that came up is that maybe the accretion process is not continuous. It's, in fact, mostly when we look at stars, they hardly accrete. I mean, the accretion rate is actually not very high in most of these T-Tauri stars. So they're underluminous indeed. We don't see much luminosity that comes as a response to the accretion. But every now and then, the disk decides to become unstable, and I don't want to go into discussion of that process. There are different models why this can become unstable in the innermost part, and then suddenly accrete onto the star and heavily increase the accretion rate onto the star. So the idea would be that, in time, this is the logarithm in time axis, this is the protostar type 1, class 1 phase, first million years maybe, or a bit less. That we have accretion, that's the accretion rate here, that we have episodic accretion, bursts of accretion where a lot of mass falls down on the star for maybe tens or maybe hundreds of years, and then it's turned off and we have very little accretion. And that's mostly when we observe stars, because most of the time they are not heavily accreting. But they do get the mass, and but only in episodes. So and then of course it's fewer and fewer until the T-Tauri star is formed, and then we don't have much of this anymore at some point. Now, do these stars exist? Never, although most of the time stars are not in this, maybe not in this episodic accretion phase, maybe we can actually find one or the other, and indeed they exist. They are thought to be stars in a heavy accretion phase that is exactly solving this luminosity problem. These are a priori outbursting variables, a priori variables. You see light curves here of several of them. Some are very, very well known now, very well studied. They're all normalized the same starting time, but some of them started almost 100 years ago. You see light curves, basically magnitudes in astronomy. They come from a quiescent phase and then they burst, some longer. And one of them is actually bursting all the time. It stays high. It went up by a factor of 100 in luminosity and is bright since shortly after 1930. So it's been bursting for about 100 years. But it will turn off at some point, and then maybe for the next 10,000 years it's not in this phase anymore. So that may be an interesting a solution to the luminosity problem. See also these outbursts also change the chemistry in a disk. These are cross sections through the disk. The upper half shows the gas phase, radius and vertical direction. The lower half shows at the same time the ice phase chemistry, the abundances from chemical networks. You see just an arbitrary molecules, here H2CO. You see the abundance of molecules before the burst here. During the burst, it's completely different. You see suddenly an increase here of H2CO at between 10 and 100 AU in the gas phase, but you see that the ice phase has been eliminated. There's no ice anymore. That's because the disk is warmed up by this bursting behavior of the inner disk. And then, after a while, it may go back to the original situation. So you can also see how disks change their chemistry because of these bursts. Good. Now I have to finish, and time is almost over. at some point the whole process takes an end, like everything. This is a very delicate process. If it's too fast, we miss the opportunity to form planets. If the disks disappear too early, we have no planets. And magically it seems to work. We do have planets, we have a lot of planets, of course. And now comes the question, well, what do we see in the disks? Let's do a little bit of statistics first. This plot here shows different clusters of forming stars in different star-forming regions. And what is shown here on the y-axis is the fraction of young stars that still have disks. As you see them in the SCDs, in the infrared spectra, as I've explained earlier. Now you see that at the age of about 1 million years, most of the stars, 80% in this cluster here, have disks. But at 2 million years, or maybe 3 million years, we are already down at 50%. So these disks go away, they disappear somehow. And at 10 million years, almost every star in those older clusters are just naked stars, there are no disks. Now, meanwhile, this is the same statistics now for transitional disks. That's those that begin to form holes and gaps and begin to dissolve, essentially. They increase, not surprisingly. So, of course, then it's, the sum of stars is given. But if the fraction of disk stars goes down, you have more and more transition disks, and of course eventually you also have to add those stars that have no disk anymore, especially here beyond 5 million years. So why do disks go from a full disk stage into a transitional disk stage with gaps and holes? Well, there are many ways of doing this. The most prominent ones are, well, planet formation, because planets need mass. So they may produce gaps in the disk, as I've shown before. Then, of course, also we have the accretion process. Material flows toward the star. That is, of course, disappearing as well. That's actually added to the stellar mass. And it can even be measured how much this is, as I just showed in these outbursting stars, for example. But another process is very, very important, and it's thought to be a really very dominating process in destroying a disk, and that's the photoevaporation process. And that's basically the last thing I want to discuss here. The stars, the Tauri stars, I've shown you that before, they're also sources of X-ray radiation, ultraviolet radiation, and especially this high energy radiation that comes from the corona of a star. Affects the disk surface massively by ionizing the disk surface and by heating it, beyond what you would expect if you had no X-rays. And that may lead to a situation where the surface of the disk is heated so much that it boils off, it boils it's moving into space because it's too hot. Now, how to estimate this, I want to show you briefly. Well, I should probably skip this as well. This shows maybe just on the left, this would be ionization. I'm skipping this. This is a temperature profile through the disk. On the left side, we have the disk surface, and we go into the disk to the right. And you see temperature profiles that have been calculated using such ionization models. You see temperatures at the disk surface up to 5,000 K. That's the same temperature as the star's surface. But this is now in the disk. And only the uppermost layer of the disk, of course. But 5,000 K at 1 astronomical unit. The Earth distance from the Sun. And that may lead to, indeed, evaporation eventually. Now, let's analyze the situation quickly. What we should do, we should look at an atom. An atom that is heated develops a velocity, thermal velocity. It's faster if it's heated more, and it's slower if it's heated less. Now, at a given distance, the particle is also bound by gravitation. And so we need to find somehow a place where the energy of the particle exceeds the gravitational binding energy because it's attracted by the star. That's a very easy process. In this example here, in this definition, we actually ask the question, when is the thermal velocity of a particle equal to its orbital velocity? That's given by the Kepler's law, more or less. Just depends on the distance and the mass of the star. Where are these two velocities the same? At that moment, the particle could decide to fly against the orbit. The other way around, it comes decoupled from the Kepler motion. If you multiply the factor of square root of 2, go a bit higher than that, then it reaches escape speed. So that means the particle can fly away from the star because it's so hot. It gets lost. So that drives the wind. If you find that radius, and it's just given by solving this equation, the radius is a function of the stellar mass and the temperature at the place where you look at. And then you need to know the temperature profile, as we discussed earlier. So at certain distances, and it's usually between a few astronomical units and maybe a few tens or 10 astronomical units, beyond that, you fulfill this criterion, because gravity is very small out there. But you heat the disk enough so that individual particles, especially atoms, can move away. Hydrogen, for example, can move away. And they form a wind, a disk wind. And that carries away a lot of the mass. Just quickly, a sketch to see why this actually destroys a disk. Here's a disk. It has accreting material coming from the outside all the time. We discussed this very briefly a few slides ago. And then there is this evaporation, this disk wind that's driven by the irradiation of the disk with high energy photons. So there's some heating going on here and there's an evaporation rate. Now, as long as the evaporation rate, the amount of mass going away per unit time, here is smaller than the replenishment through accretion, not much happens. Just part of the mass goes away and the other mass will be accreted onto the star. But at some point, the replenishment of mass from the outer disk decreases because there's just no material left out there, or not much. So, but the evaporation is a totally different process. It just happens anyway, with any material that you have here. So at some point it could happen that the evaporation rate is larger than the accretion rate at this point. And at that point, you remove all material that comes from the outside, you remove it in the vertical direction into wind. And then you form a gap, because no material continues to fall toward the star, but it's all moved away. And so at a later stage, all material inside, at this moment here, that is inside, falls onto the star, and everything that now moves in to this radius is removed in a disk wind. So the disk is gone eventually. Can we observe this? Well, I skipped this, maybe shortly here. You see that a certain radius that is close to the gravitational radius, as we call it, where this effect is most important, you form the disk profile here, forms a gap very rapidly, and suddenly this gap widens and the disk is gone. Can we observe this? Yes, we can indeed. These are spectral lines of ions, of a neon ion. A neon ion can form basically only if neon is irradiated by X-rays. So it has to sit at the surface of the disk. And if you look carefully, this spectral line of neon 2 should be centered. This is, of course, from a spectrum, and that's been translated into velocity, blue and redshift, because of the Doppler effect. This line should be centered around this expected middle line here, this blue line, and you see it's actually shifted toward the blue, as we say, toward negative velocities. Velocities come toward us. So this mass, this neon, is moving from the disk toward us. It moves away from the disk. It's a disk wind. The same here, another example. You see a slight asymmetry in the line here. There's more area on the left-hand side than on the right-hand side. So indeed, eventually, that's why we form such disks. At least in this process, you see a big hole here in the disk. This is the outer disk, and we begin to remove material in the inner disk at that radius. Good. I have to stop. This is my summary. Star formation is important, as I said at the very beginning. I hope I convinced you. Star formation is not an automatic process at all. We discussed rotation, magnetic fields, and there's a lot else that makes star formation relatively inefficient. There is enough material, there is enough opportunity to form stars, but most of the material will not collapse. I need to say that as well. So it's only a fraction. But star formation is important. These are the reasons. That's what we needed to discuss the process. We need dense molecular clouds, we need gravitation, mass motion, thermal pressure, magnetic fields, rotation. And it's become a fight between, if you remember well, it's a fight between self-gravity and all other forces, because all the other forces want to expand and self-gravitation wants to contract. And to successfully form a star, we need to have one winner of the game, and it's gravitation. Good. I want to stop here and give you the opportunity to have questions, to ask questions, and go into some discussions.